The idea that causation has a special role to play in scientific explanation and criticism of that idea became especially important in the early part of the 20th century, when scientists concocted a theory, or discovered a theory, depending on how you look at it, of quantum mechanics, of the domain of small subatomic particles that suggested that causation not only wouldn't, but couldn't play the kind of role that physicists and philosophers of science had previously imagined. That's our topic for today, some of the strange and mysterious philosophical problems raised by modern quantum mechanics. I want to remind you that a problem with the, at least the deductive nomological version of explanation that we talked about last time is that it seems to suggest that anything that would fit into that schema, into the deductive nomological schema, where we have a variety of deterministic laws plus a specification of relevant conditions, that's the explanandum, you'll remember, or the thing to be explained. It says that to explain something, the best way, the ideal way, would be to show that it follows as a logical, deductive consequence from laws of nature plus specifications of initial conditions. And this seems to be fulfilled for lots of things that physicists do. Lots of the stuff, especially in the Newtonian world, can be explained in just this sort of way, showing that it had to happen. It was a consequence of the initial conditions plus the laws that govern the universe. So this is a reasonably good model. I mean, it wasn't just a philosopher's pipe dream. This is a reasonably good model of what seemed to be going on in physics. And it is an ideal insofar as I guess almost everybody would imagine that if we could produce this kind of explanations for things, it would be satisfying if we did not have to resort to the probabilistic explanations, the other type that we talked about last week. Those are often regarded as second best because they don't tell us that things have to happen. They only give us a probabilistic expectation that things would happen. And you'll remember that they suffer the problem of being explanations only with reference to specified contrast classes. Now, the deductive nomological form of explanation had a particular problem of its own. So I want to start by asking you if you remember what problem it was that we discussed. Yeah?
Using this, we can derive things but not explain them.
Well, some things that fit this model quite well, some things that we can demonstrate the necessity of using a model just like this don't seem to provide explanations. So not everything that fits this model is an explanation. And the example we gave had to do with a flagpole, knowing the position of the sun, the laws of optics, the height of the flagpole. We would be able to, with that information plus some other background presumptions, we would be able to deduce the length of the shadow produced by that flagpole. And so we would thereby have explained why the shadow is just that long. It has to be that long, given the way optics works, given the laws of nature about optics, plus these initial conditions, the particular position of the sun right now and the height of that flagpole. So that works out okay. But there's an asymmetry. You could also do the following. Given the length of the shadow, the position of the sun, and the laws of optics, you could also deduce from that information the height of the flagpole. Right? Okay. And the problem for this model of explanation is that while it fits the model perfectly, it doesn't seem to provide an explanation. I mean, it seems bizarre to imagine that the reason that the flagpole is that high is because the shadow is this long, the position in of the sun is just so, and the laws of optics are just so. There seems to be an asymmetry there, and so one asks the question, okay, what makes, since they both fit the deductive nomological model, what makes the first one seem like an explanation and the second one not? And what some people might suggest is the key factor is that there is some kind of a causal arrangement that works one way rather than the other. The shadow is caused by light being blocked by the flagpole in a particular way. The height of the flagpole isn't being caused by the length of the shadow. So the critique is that deductive nomological explanations, while they offer us an interesting framework within which explanations often may be fit, they don't give us a sufficient condition for explanations. That must be provided by something else, and the particular something else that some have suggested is cause. We've explained something not only when we can fit it into a schema like this, but when we've shown that the explanans accounts for the cause of why this happened, or why this comes about, whether it's a particular case or a general rule. So causation seems to play a fundamental role, at least in traditional sorts of explanations. We want to know not just whether something can fit into a logical framework like this, we want to know about the causal links. And when we talked about Aristotle's four causes, you'll remember when we talked about the efficient cause, and also when we talked about the material cause, those are particular styles of explanation that have been extraordinarily fruitful, and they have been the major focus of attention, at least within physics, up until the present century. So cause has been thought to play a fundamental role. The reason I wanted to bring that up again this time is because that's just the problem that some people have seen with quantum mechanics, because it purports to offer and seems in some sense to give as good explanations of a particular domain as have been had in any theory, and yet it doesn't really talk about causes. It, as a matter of fact, specifically in some of the key elements of the theory, specifically argues that such talk is, at least it's a conservative way of putting it is to say such talk is useless. A more radical way of putting it is to say that quantum mechanics suggests that such talk is simply inapplicable at the quantum level. Now, I want to give you a quick sketch of what the atom, I can't say looks like, but what the atom is held to be, just to get us on the right footing. The Bohr atom, which was born in 1913, was an attempted solution to a particular kind of problem. In every case, by the way, throughout this whole development, the physicists involved, for the most part, were very resistant to some of the counterintuitive moves that they felt that they had to make. The reason in each and every case that they felt they had to make them was because there was no other way to explain experimental data, at least not that they could see. And so in each case, these changes in the story of the atom are driven more by experiments, more by phenomena that people have found out about in the laboratory than they are about in pure theory. That makes this story different in an interesting way from the story of relativity theory, which is driven to a greater extent by just an effort to try and systematize and organize a theory rather than to accommodate physical data. The problem with quantum mechanics was that there were so many different things that they'd learned, and the history of atomic theory from 1900s, say, up until 1927, there were so many different things that they learned. It was very difficult to bring these together in any kind of a coherent picture, in any kind of a consistent picture. First, they just had a motley bunch of hypotheses and conjectures and ideas which tied on in some cases to classical theory. In other cases, had to take radical departures from classical theory. Then in the 20s, the mathematics, the mathematicians kind of threw in their 2 bits, and so that there was it was possible to offer a mathematically coherent picture. They were able to bring all this together in a mathematical theory that at least made mathematical sense. But again, the physicists involved, especially people like Pauli and Heisenberg and Bohr, were very suspicious of the mathematics. They wanted to know, what does all this mean physically? And so when we get to their final conclusion, which is weird enough, I want you to understand that the people who were crafting this were not particularly eager to part company with the traditions of physics, but they had to do that. They felt they had to do it in order to make sense of the experimental data. Now, the Bohr atom, as it was constructed in 1913, had to solve a particular kind of problem. Just before 1913, Ernst Rutherford had offered a model of the atom that explained a great body of the experimental evidence. And the model suggested that atoms looked like this. According to Rutherford, you had positively charged nucleus and electrons going around. They're very small. They're not that big. Electrons going around the nucleus in orbits. Okay. The problem was this. On traditional Newtonian, well-confirmed, incidentally, physical laws, if something's going around in an orbit, if it's moving like that, it's got to be losing energy. It's got to radiate. That particular motion requires that energy be lost. It is accelerated motion. And so, so according to classical physics, those particles are accelerated as they go around the nucleus, and they should be losing energy. But if they're losing energy, then they should also be spiraling into the center. They should collapse. There should be no stability of atoms at all. And it's possible even to calculate just exactly how long an atom should last. And I believe in the case of the hydrogen atom, it should last about 1/trillionth of a second, which would make for a very, very short history of the universe. If all the atoms were collapsing into their centers, we wouldn't be around to agonize about it. That would have happened quite some time ago. The Big Bang would not have gotten off the ground. So obviously, they're not doing this. They're not doing this at all. How is it possible? Okay. Bohr offers a model of the atom which still has positive nucleus and electrons going around in what he still took to be circular orbits, negatively charged electrons. But he suggested something rather strange. He said, okay, they are going around like that in orbits, but they are not losing energy. They are in stationary states. They're orbiting, and there may be many of them. And he even postulated, I think as early as 1913, I'm not absolutely sure of this, I think he even made at least a suggestion that conceivably some of these orbits might not be circular. There might be some of them that are elliptical. Later on, it was determined that on this model, there would be elliptical orbits. That you'd have to have those to account for certain phenomena. But he said, OK, we're going to have associated with every atom a bunch of discrete stationary states. So that, for example, with a hydrogen atom, there could be one electron at this particular level or orbit, or alternatively, it could be out there. When it is in either one of these, it can't be in both, but if it's in either one of these things, the whole atom will not radiate, does not lose energy. That's the sense in which it's a stationary state. Nonetheless, for other empirical reasons, he still had to talk about the electrons orbiting in order to account for other phenomena. So the electron's orbiting, but it's not losing energy. Whenever it moves from one of these stationary states to the other, or from one orbit to the other, if you like, that's the only time when an atom will either gain or lose energy. It's in those transitions. And when they gain energy or lose energy, they can do this only in a particular quantity. They do not go gradually from this orbit to that orbit. They do not make transitions gradually from one energy level to another. It's blip. They either accept, that is, absorb energy from the outside in unit amounts, atoms of energy, if you like, or they lose it by those amounts. They can never lose it by a half quantum. They can never gain it by a half quantum. And they do not gradually go from one orbit to the other. They leap. Now, on this model, notice, on this model, which is visualizable, it's a model that talks about orbits at different distances from the nucleus. What that means is that when an electron goes from there to there, it does not occupy the positions in between. Now, here's what I want you to know about that Bohr atom. On the one hand, it continued to try to make use of some kinds of classical concepts. It still talked about when the atom was in one of its stationary states. It still talked about the motion of the electron in a kind of a traditional classical way. It was an orbit. And this explained a great deal. And the whole picture was, again, one that involved distances from the center, transitions from one place to the next, movements, continuous movements in this orbital pattern. All of that looked pretty traditional. But here were these glaring, glaring departures from traditional physics. One, I've mentioned the two main ones in 1913. One is that even though these electrons are in orbital motion while in stationary states, they are not losing any energy. That's a gross violation of classical physics. And two, when they make these transitions, it is in discrete amounts. It's quantized. And they do not occupy positions in between. They do not occupy energy levels in between these discrete possibilities. The picture I want to leave with you is this one. I want you to remember this Bohr visualizable atom, which on the one hand tried to talk about it as if it was a little miniature planetary system, but then on the other hand, it had features that were like no miniature planetary system could have. This explained, among other things, why it was that the orbits didn't deteriorate and why the electrons didn't crash into the center, because that's not the way electrons work. It explained also, and I'm not going to try and tell you how it did that, but explained also such things as spectral data about the different elements, so that when you take different elements and you heat them up and you cause them to radiate light. I mean, that's what happens when that's what these lights are doing, right? We've heated up little wires in the light bulb and they're making light. But when you take different elements, make different filaments in the light bulbs out of different elements, they'll radiate in different wavelengths and they'll have characteristic little patterns. And they'll also have gaps. There'll be gaps. There won't be a continuous bunch of wavelengths. You won't just see it going, well, it's getting stronger and stronger toward the yellow. It won't be like that. There'll be sharp lines, okay? And these gaps are now explainable mathematically, precisely. He can predict exactly what the gaps should be like on the basis of this theory. Now, this Balmer series, as it's called, of spectra for the elements, for hydrogen, that's what the Balmer series was, plus some elaborations that had been made by a man named Rydberg, this had been known. It had been known that you had these characteristic spectral patterns and that there were these gaps. And they knew quite a bit about them, except why in the world that should be. And the Bohr atom seemed to explain it. He says, if things are the way that I suggest, then that would explain why we get these particular patterns. And indeed, Bohr was able to predict what certain gaps in the spectral patterns should look like. He was able to predict, for example, what the spectrum of hydrogen should look like in the far infrared and the far ultraviolet, which hadn't been tested yet. And when it was tested, it went pretty much like he suggested. He was able to correct some experiments. People had said, no, you can't be right, Bohr, because we've got some spectrums here for hydrogen that you didn't predict, that your theory doesn't predict. He says, he looked at them and said, well, seems to me that I could explain that only on the assumption that you've got some helium mixed in there. So they went back and checked it out, and lo and behold, had some helium mixed in there. And then that didn't quite solve all the problems, and he said, you know, and among the helium that you got in there, you've got some ionized helium in there. That is, helium from which one of the electrons has been stripped off. They did. You know, they were able to confirm very, very precise predictions about what he said had gone wrong with experiments that supposedly contradicted his theory. And this pretty much went on through the teens. The reason for the theory was to explain experimental data and to make it make sense. It also was, you know, as I say, there was this systematic consideration. The original problem was, how come these orbits don't collapse? But by the 1920s, this whole picture was becoming very difficult to juggle. And the focus of attention was directed toward the attempt to do two things at the same time. Offer this kind of classical picture, while at the same time departing in a major way, from classical presumptions. And it was in the 1920s, in order to try and bring some coherence to it, that a number of physicists, especially Pauli, Wolfgang Pauli, a number of physicists decided that they should abandon all these classical presumptions, for the moment anyway, and just try to figure out how to explain the observations. That's all. Is there any way to bring order or organization to these observations? And we want to try and make sense of them. And maybe the thing, actually this isn't original with Pauli or even original in the 20s. I think everybody has suspected this all along. Maybe the problem is in our classical expectations. The idea that we should be able to build pictures like this of what's going on at the atom. The approach, as I've mentioned, that was taken up through the 1920s was to try to see if sense could be made of the observations, or if we could gather them together and find some coherent way to speak about them. And a coherent way to speak about them in physics means usually a mathematical language. And so they were looking for a mathematical language, while at the same time being very, very worried that it's going to be so formal and abstract that they wouldn't understand the physics. And so there's this tension among the physicists, in probably within each of the physicists, for that matter, a tension between, on the one hand, trying to offer a pure, abstract, mathematical account that will predict, if you like, or do justice to the data that they had, while on the other hand, wanting to know what in the world it all meant. I mean, so the pure abstract mathematics is something that well, the mathematicians loved it, but the physicists themselves were alternately attracted to it and resistant to it. They really wanted to have some kind of a physical understanding. What I want to make clear out of that is that something that probably you experience as well. I mean, you can be told that here's a formula that works, here's a formula that produces a certain result, or here's a formula that you can use to for some purpose or another. You can know all that stuff. You can know that it works great without having any kind of a real understanding of what's going on. And in our case, when we're learning new techniques or when we're learning new proofs, we're presuming that, well, it's just because of our lack of experience with the stuff. Our teachers, surely, the people who are teaching us these techniques, they have this understanding. And it's just a matter of time before we get it ourselves. Well, for the physicists who are working at the state of the art, at the edge of the discipline, it sometimes seemed to them that they were in the same place that a novice would be. They had all these formulas that seemed to work, but they didn't really understand what they were doing. By 1927, though, both Heisenberg and Bohr began to try and re-inject. This is after after quantum mechanics as a formal mathematical theory has finally been worked out. And with some it's been worked out in many independent directions. People who thought that they were saying the most radically opposite things offered mathematical interpretations that turned out to be formally equivalent, which gives tremendous support for each of them. I mean, in this particular case, there was a Heisenbergian, and Heisenberg and Max Born and another man named Pascual Jordan worked out, mostly Born and Jordan were doing the mathematics. Heisenberg at this particular point was really, that was one of his moments of being very, very upset by the purely formal character of the mathematics, but he was working with these other guys who were really excited about mathematics. The three of them produced an interpretation of quantum mechanics that worked out very nicely in predicting some of the fundamental features of quantum mechanics, but it was pretty much based on the idea that these electrons and light and everything can be analyzed as if they are particles. At the same time, an entirely different analysis came along, which caught the attention of all those people that didn't like all this discontinuity in nature. Erwin Schrodinger produced an analysis of the whole, also of the whole domain, which looked for all the world as if it suggested, and Schrodinger thought this, it looked for all the world as if it suggested that everything was waves, was wave-like, not particulate, but behaved instead, spread out in space and propagated in a wave-like manner rather than, bulleting in like a particle. Schrodinger actually argued against the whole idea of these quantum leaps. In one gathering in 1926, I guess it was, quite apart from the fact that these quantum leaps were extraordinarily well confirmed. It was not something that I think he should have had any basis for doubting, except that in that particular case, his theory was uncongenial to these quantum leaps. But what he was able to do was to offer a mathematical theory that was sort of based on a wave interpretation of matter. He had a hot argument with Bohr, who had this quantum interpretation of matter. And yet it also turned out, Schrodinger knew it, that mathematically these two theories were equivalent. Now you'll remember from the verificationists, especially if two theories were equivalent in that way, and especially if they were empirically equivalent, in other words, they predicted the same experimental observational data, then there really wasn't any difference between them. And there were positivists in the crowd. Again, Pauli was pretty much a positivist in this group. And he said he would have argued that anything we say that goes beyond the observables is at least something we should avoid for now. Let's put it that way. We should avoid that for now. I want to try and be fair to Pauli. And so here are these apparently very different approaches that seem to have very, very different implications, but that were mathematically equivalent. But the mathematics got worked out within about a year, so that there was sort of a single general treatment that borrowed some from the Heisenberg treatment, that borrowed some from the Schrodinger treatment. And it was in about 1927 when all this mathematics got on at least the nerves of Heisenberg and Bohr, and so they came back to try and figure out what it all meant. So what I want to do is to leap to some of these philosophical or theoretical or interpretational features of quantum theory. We will come back to the formal mathematics in due course by the end of the lecture. But right now, I want to talk about some of the things that are more easy to talk about, namely the rationale or the interpretation given by Bohr and Heisenberg to their physics, to the physics that they'd worked out. Keep in mind, though, that it's a very different thing to talk about quantum mechanics as this formal mathematical theory, on the one hand, and as this prose interpretation that I'm going to give you on the other hand. The mathematical theory is extraordinarily well confirmed. It has done all the things that the verificationists and the falsificationists would ask of a theory. They have suggested ways in which it might be falsified, and it hasn't been. It has offered all kinds of offered explanations for an array of things that could not have been explained otherwise. It has been the basis for technologies that have been remarkably successful. It is, for these 65 years since 1927, it has been probably as successful as any theory there ever has been. It is a remarkable theory. That's the mathematical theory. But physicists disagree about the interpretation that's to be given to it, the prose. So what I'm about to talk to you about is stuff that's controversial to a certain extent. And there's many physicists who'd say, to hell with trying to understand what's going on, or let's just put that to the side right now to try and put that into intuitive terms. What we have here is a powerfully designed and a powerfully confirmed mathematical theory. That's really what quantum mechanics is all about. We'll come back to that one because it's a very interesting. There's a very interesting sort of epilogue that I want to tell of the whole story at the end that involves it. But one of the things that was kind of a capstone on the mathematical theory was this. It's Heisenberg's uncertainty principle. P is usually momentum. Y, it's P, I've forgotten. Q is position. So this, let us say what we're interested in talking about are the positions and momenta of things like electrons. Now that's a classical question, and we're wanting to know about, it sounds like we want to know about a particle, where it is and how fast it's going. Momentum is just mass times velocity, and the important thing here is the velocity bit. Okay. So we want to know how fast it's going, we want to know where it is. The delta indicates what again, Carl?
Delta indicates like how certain you are about what the momentum is.
Okay. Here is a fundamental axiom, postulate. It's not just some small feature of quantum mechanics. This is part of the formal theory, but a fundamental part of the formal arrangement of quantum mechanics is this formula, which says, roughly, the precision with which the momentum can be measured. I'm going to give it to you in one version right now. The precision with which the momentum of a particle can be measured is inversely proportional, it turns out, to the precision with which the position of the particle can be measured. Let me just put it in a different form here. I can divide both sides by delta Q. That's still our constant. And that's what I get, right? Okay. There's the inverse proportionality. What it means is, now notice that if this number gets large, then this whole number gets small, right? So as this number gets large, since this is approximately equal to it, this number gets small. As this number gets large, this number gets small, and vice versa. As this number gets large, this number gets small, right? So what it says is that the more precise the measurement of one of these two variables, these are just a characteristic pair of what are called conjugate variables. Okay. Others are the energy of the product and its time. Okay, there are others. Whenever you get these, you get these pairs of so-called conjugate variables in quantum mechanics, gaining precision in your measurements of one of them costs you in terms of precision that's even possible in the other one. So what you can't know, this is the first way I'm going to put it, in terms of knowledge, this is an epistemological claim. It would appear on the basis of this, a reason for adopting this, by the way, is that if you adopt it, you can show as a consequence some curiosities about the way that the quantities have to be multiplied within quantum mechanics and a number of other factors. But the whole system can be worked out in such a way that this plays an absolutely fundamental role in deducing other things, in other words, in explaining, again, on something like the deductive nomological model, of explaining many, many other things that are known to be true. Some of these things are observables, I mean particular experiments, and some of the things that can be explained or deduced from these presuppositions are laws, generalizations that are known to be true. So we are resorting to something that looks like, at least in terms, at least at this level, looks at least vaguely like the covering law model. The explanations of, remember, there's two different renderings of the covering law model. Some things may be explained deductively, other things not. So I'm going to put probabilistic law. I'll put P for that. P2, P3, ... Pn, plus initial conditions. You can, on the probabilistic model, you can explain with, probability distributions of things, or you can explain an event with some degree of probability, but both of them have the same structure. Laws, initial conditions, put together, yielding the thing to be explained. And what in a way, in seeking for explanations of the quantum domain, there is something like this that seems to have been going on. Heisenberg was satisfied that that his uncertainty principle must be true because if it were true, then so much else could be explained as a deductive consequence of it. That it was, at least at one level, it seems, another way of putting that is that it captures many curiosities in one fell swoop. As I said, in Heisenberg, that was the formal reason for making this proposal in the formal theory. In February of 1927 or so, independently, he and Bohr started trying to put together some kind of a intuitive understanding of this. The way that Heisenberg did it was something like this. He said, "Now look, let's just see why this might be the case." I mean, just kind of in intuitive terms. It turns out this is a very definite mathematical result, but forget about the math right now. Why should it be that at that particular level there should be this odd give and take between the measurement of one variable and the measurement of the other? Well, he said, let's say we want to look at a book. put it there, we'll shine a light on it. And the way we look at it is to allow light to be reflected off it, and that's what looking is all about. There are other things we can do to examine this book. It doesn't have to be visual. I do that with the book. I flip its pages. I learn something about it like that. I mean, I touch the book. I learn things about it like that. But anytime I look at or examine anything in the physical world, it involves an interaction of that kind. I've got to interact with it. And it usually doesn't matter. Now I'm going to jump to something that Bohr later on started talking about because it is relevant here. One of the things that in classical physics was held out to be the hallmark, I think I may have mentioned this earlier on, the hallmark of physics was its objectivity. Physics is objective in the sense that it manages to control, you know, what it talks about is usually ideal in at least this sense. I mean, the theories of physics are demonstrated in laboratory experiments by and large. Physics doesn't say, for the most part, you can prove my theory right or wrong by just going out and looking at the world. That's a little bit too uncontrolled. A physics experiment, which is supposed to test a theory or examine the world, is performed under the most excruciating controls. I mean, an extreme degree of carefulness in trying to make sure that what you are looking for is not interfered with in any way by external variables. The laws of physics are true, all other things being equal. And what you do in the experiment is you try and make all other things equal for the purposes of the experiment. So that you want to try and examine something in some sort of pristine, objective state, as it is undisturbed, especially by you. I mean, you want to try and, that's what objectivity is you want to try and put whatever you're examining at arm's length and not interfere with it, and that permits you to see how it really works, how it works all by itself, as it were. And that has always been an ideal of physics. That's actually what objectivity means, in a certain sense. That the experimenter is not bringing anything into the situation that disturbs it. That the object of the scientist's interest is something that is just the way it would be if nobody were looking at it. Now, just to continue with that for a second, a major difference between the natural sciences and the social sciences might be held by some to be just, you know, the reason why social sciences can't be so precise is because of the subject matter, probably, but that's not, that doesn't give us much information. What is it about the subject matter of the social sciences or the necessary procedures in the social sciences that make it different, less hard-nosed than physics, for example? Well, take anthropology. Imagine that we are trying to examine a tribe. It is impossible to get any of the kinds of information we need about their practices without interacting with them in some way or another. So interaction is necessary in that case. Well, what happens at the quantum level is that you're talking about things that are so tiny that you cannot possibly examine them without massively interfering with them. An electron is tiny enough so that, for example, if you were to try to look at it with an electron microscope, I mean, that's like shooting a billiard ball at another billiard ball. I mean, you have to bounce something off of it to see it or to record it. You have to interfere with it in some way to know what it's doing. That's what observation is all about, is interacting with phenomena in a certain kind of way. When we get down to the quantum level, we cannot interact with it without massively disturbing it. Let's say we want to measure its position. We have to put up a Geiger counter or something, a screen. If we want a real precise measurement of its position, we have to have a fairly elaborate setting. I mean, a Geiger counter will tell us that it hit somewhere around over here. Okay, what we need, if we want to know what its exact position is down to the order of magnitude of an electron, there isn't anything for it except to shoot something about the size of an electron at it. I mean, that's what you need to do. You have to have some kind of device, a measuring technique that's as fine as the electron itself if you want to know what its position is at that order of magnitude. And you can't get much smaller. So you shoot your electron in there, you're bound to disturb the movement of the electron. So there is why you cannot know, if you know the precise position of the electron, why you can't know its momentum, because you've stopped it by and large, or you've altered its momentum. You must necessarily alter the momentum of the particle in order to know what its position is. And there are experiments that you can set up to get very, very good readings of the momentum, but the more and more, the better and better these readings are, the less and less you'll know about the position. Because to know the position, you have to do a certain kind of experiment. To know the momentum, the velocity, you have to do a certain other kind of experiment. And doing the one precludes doing the other. You can't do them both. Not on the same device. So, at this particular level, this epistemological level, where we're talking about knowledge, this is the kind of consideration that Heisenberg offered and then Bohr later reiterated about why it makes sense that we can't know in principle. We can even talk about exactly how these two things relate, because at that level things can be made very, very precise, at least in terms of our calculations. We can talk about the precise mathematical relationship between knowledge of the position and knowledge of the momentum. And it can be calculated out to be precisely this. And you don't measure knowledge, but it has experimental consequences that can be borne out. So that's the epistemological interpretation that's being placed on this particular, this principle of Heisenberg's, the uncertainty principle. However, you might wonder whether there even is such a thing. This is not epistemological anymore. This is metaphysical, if you like. Whether there even is such a thing as the simultaneous position and momentum of a particle. Because given the fact that this uncertainty principle plays an almost axiomatic role in quantum mechanics, there are no places in quantum mechanics to talk about the simultaneous position and momentum of a particle. It is not possible. It's not within the theory. It doesn't have a mechanism for even talking about such things. It doesn't refer to such things as simultaneous position and momentum of a particle. Indeed, what it does say is precisely that there can't be any such numbers, because any precision you have on here has to satisfy this equation, right? So that there cannot be equally precise, perfectly precise. You can have you have 50-50. But you can't have perfectly precise measurements of both of them. If one is perfectly precise, the other one has to be very, very vague and perfectly vague. You have to have, if you want to have a perfectly precise calculation of either of these variables, you can do that at the cost of having any information at all about the other one. At least that's the way the principle goes. So here we've got a theory that doesn't refer anywhere to such things as the simultaneous position and momentum of a particle. It doesn't talk about them. It doesn't even allow talk of them. Bohr, I know, was mightily disturbed about this. Heisenberg also needed to have a kind of a philosophical understanding of what was going on, given his frame of mind. He wondered whether we should even try and think about such a thing as the simultaneous position and momentum of a particle. For he reasoned as follows. What is a momentum? Well, it's really, what we're concerned about is velocity. Velocity is not something that makes even any sense in a literal spatio-temporal instant. What velocity makes sense in is between there and there. Movement. It's a measure of movement. It's a measure of motion. It has to do with things that have paths, things that move in space-time. Things that have no such motion, how can they have velocity? I mean, if we're worried here now about intuitions, how can they even have a velocity? So maybe when we pin something down, his argument went like this. Maybe things like velocity are like pressure and heat, which were well explained in the 19th century as statistical phenomena. You explain pressure by imagining that a gas is filled with molecules in motion and they're constantly banging on the walls. You heat up the container, the molecules move faster, that's heat, and they also bang on the walls harder, more pressure. Those are statistical phenomena. Heat can be understood as the mean kinetic energy of these different molecules in any particular gas. That's what heat is. That's the way it's interpreted in traditional physics. And the molecules aren't themselves hot, right? Because they're banging up against the walls. Heisenberg suggested maybe, his first step, maybe something like momentum is like that. Maybe it's something that can have a meaning or an interpretation only at the macroscopic level. We shouldn't expect electrons to have these characteristics because these characteristics are explained by things that electrons, whatever they are, do. Bohr offered the idea, well, what we cannot altogether abandon these kind of intuitive, classical, philosophical, whatever you want to call them, pictures. We can't do that. We can't abandon them completely. That's the only way we really get understanding. He was one of those physicists that demanded to have something like that. Einstein was another. They didn't disagree about this. What we need to do, he said, is to see that at the quantum level we can have now this picture, now that. We can look at things as if they're particles, or we can look at things as if they're waves. We need both pictures if we're going to have anything like a complete portrayal of what we know. We need to look at it in both ways, but we cannot look at it both ways at the same time. So we show the particle-like character of the quantum domain by doing certain kinds of experiments. In those experiments, it will not be possible to see it as a wave. It will not look like a wave. It will contradict the whole idea of being a wave. Or we can do other kind of experiments in which we expose the wave-like character of the phenomena. In those experiments, the results will contradict the idea of its being a particle. It will behave in a certain way depending on the experiments we set up. It's not reading our minds or anything like that. It's just those kinds of interactions expose something about the basic structure of reality that we call wave-like. And the other experiments expose something about reality we call particle-like. Waves and particles are our pictures. They are macroscopic pictures. They contradict one another. Their predictions, what they say will happen, contradict one another. Contradiction is our problem, too. That's our way of thinking about things. The real world is such that it will not bend. It will not bend to either our logic or to our need to picture it. And we would be giving a false account of reality if we pretended that it could. All we can do is to say, it looks now this way, now that way, depending on what we do. We can describe things causally, or we can describe things in terms of spatiotemporal position. We can't do it at the quantum level. We can't do it both at the same time. At the macroscopic level, it all works out because these are statistical phenomena, and for the most part, at the macroscopic level, everything kind of some of the problems cancel one another out, and we can actually talk about objects and their positions and their simultaneous positions and momenta, because we do not need the kind of precision that we need at the subatomic level. These are all just statistical aggregate figures. In any case, so we've got, that's called the complementarity principle of Bohr. So we've got Heisenberg's uncertainty principle, which actually is part of the formalism. Then we've got his explanation of what it all means. And we've got Bohr's complementarity principle, which really does kind of organize how we're supposed to go about our business in investigating nature. But it is really pretty philosophical. It's really an interpretation. It has consequences in the formalism, but again, what you make of this fact needn't be the same thing that Bohr made. And it was in light of that that the interchange between Einstein and Bohr began in 1927 at a conference in October of that year, Solvay conference, and there was another conference in 1930, and then there was a major paper that that Einstein, Podolsky, and Rosen wrote in 1935, all of which had this upshot. They were trying to say quantum mechanics isn't complete. And it's a fairly simple argument, which I won't sketch right now. I don't have the time to do it. It's a fairly simple argument, even though the details look hairy. But they argued that it's not possible. I mean, it's one thing it's one thing to say that we can't know the simultaneous position and momentum of particles, for example, since that's been our example here. It's one thing to say you can't know them. It's really quite a different thing to say that they aren't there. And there's reason to think that they are there, because we can predict the position. And then in another experiment, we could predict the momentum with arbitrary precision. We can't just do it at the same time, but that seems to imply that on the basic assumption, I'm going to read their basic assumption, that seems to imply that the thing has these characteristics, these values. Here's the basic assumption that is quite philosophical, but it's the basic presumption of the Einstein-Podolsky-Rosen experiment. I read from the article. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. That's all. If you can predict the value of a variable or a quantity with absolute certainty without disturbing the system, then that's real. It's physically real. Simple, modest assumption. And Einstein, Podolsky, Rosen tried to show that if that's true, if that's right, then quantum mechanics isn't complete. That's all. In 1964, a theoretician named John Bell. But what he showed was that this little assumption that I read to you in the Einstein-Podolsky-Rosen experiment, namely, that a sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing a system. That assumption has consequences in a whole class of experiments, real experiments that can be performed, has consequences that conflict not with Bohr's philosophical interpretation, not with Heisenberg's philosophical interpretation, but which conflict with the quantum mechanical formalism. Aha, maybe we can perform an experiment. That was in 64. I think it was in 81 and 82. I'm not exactly sure of the dates. A team of experimentalists led by, I think, Elaine Aspect is his name, performed a whole series of extraordinarily elegant experiments in which they tested this definition of reality against the quantum mechanical formalism, because they each predicted different things. The quantum mechanical formalism wins. Among the many philosophical problems raised by contemporary quantum mechanics, both for philosophers and for scientists in practice, are questions about distinctions between the observer and the observed. Quantum mechanics sometimes seems to suggest that there is no hard and fast distinction between the scientist and the experiment, or at least between the scientist's instruments and the things that the scientist is investigating. And this, in turn, begins to raise questions about objectivity. Is science truly objective? Is science neutral on value questions? Those are further issues that need to be discussed.